When two waves are present in the same medium, we can only see one effect, because there's only one medium. We call the combination of two waves a superposition of them, and it's actually as simple as can be. At every point, the strength of the superposition is just the numeric sum of the strength of each wave. So here we're going to generate a red wave and a cyan wave inside a single string medium, and where they overlap we only see their sum, which is marked in yellow. So right now both of those pulses are 0, so their sum is 0, and the whole thing is just the yellow line. But now we'll generate these two, and as they come together we see how they add up, and we see their sum. We'll see one more time. So we see at this moment the wave would be this, and then this because the cyan is 0. Here's this bump, which is their sum, and then this like that. Sketched kind of badly, but this is what the actual medium would look like, something along these lines. You wouldn't be able to see these bits. You wouldn't know they're there. You just see their complicated disturbance of the medium. Where the waves have opposite phase, they quote-unquote cancel in whole or in part, yielding a wave smaller in amplitude than either. So we see here, they have opposite phase, and in the middle we have lesser amplitude. Let's say here, lower amplitude than either. When we say cancel, we need to be careful because, as you can see afterward, afterward you have that the waves have just become exactly who they were, and there is no sign that they've gone away. So they only cancel in the moment. They don't destroy each other. They actually just pass through each other, but their effects seem to cancel out, at least a little bit. And again, we see we get a sum. They're both 0. Here we have just the red one, and then we start taking off the cyan one. So we get here. Now we have just the cyan one, and then back to both being 0. Of course, this is because they're finite pulses, and if they were continuous waves, it would look more complicated. We'll get to that in a little bit. This is particularly interesting when the two waves are out of phase, but happen to be equal in amplitude. So we can watch here, because of what happens in the middle. In the middle, they start canceling out exactly, and there's a moment where they've canceled out completely. Also keep your eye on that point. It never moves. The two waves happen to pass and are always opposite at the moment we're at that spot. At the instance they exactly overlap, it looks like there's no wave at all. If we were to take a picture, it would just be a flat medium, undisturbed, and we wouldn't know that there was a wave in it because waves are intrinsically time-based, so we'd have to see a little bit later as we moved on. This would mean, since there's no distortion in the medium, there's no potential energy storage in the medium either. It's entirely kinetic at that point. The two waves pass through each other without interacting. They don't bounce off each other or share energy or anything of that sort. Confusingly, because we haven't chosen the words particularly well, we say that the two waves interfere. In English, two things interfere when they get in each other's way, but in physics, two waves interfere when they adjust the medium, but they don't affect each other. When the waves have the same phase, we get what's called constructive interference, and the resulting amplitude is greater than either one. Where the waves have opposite phase, we get destructive interference, and the resulting amplitude is lesser, or could even be 0. Despite these names, the waves aren't destroyed by destructive interference, they just pass through each other. It's only at the moment they seem to have been destroyed. Consider the moment the two centers coincide. Draw a blue circle around the case or cases with the greatest amplitude, and a red circle around the case or cases with the least. I'm going to continually draw the left one overlapping the right one. Really, they'd both move over, but I'm going to pretend, even though this guy would move over and this guy would move over, and they would meet here. I guess we can do that once. So we would have let's try that. The lower guy would look something like that. That's the leftward moving guy. The rightward moving guy would look something like this, moving that way. And therefore, together, they would be 6 high. If we talk about the part B, we would have, if this is their center, then it extends 2 on either side, going that way. And this extends only 1 on either side. So their combined would be 4. For part C, I'm now just going to draw. I'm going to draw C and leave it where it is, and have the other guy who would be, this is the center line, goes up to 4, so it would be something like this. And we can see that where we add them, we have +4 plus a -2 ends up at 2. Something like that. And then this one, again, we'll leave the blue one alone. The green one goes like that, and we end up with no wave. So it's pretty clear that the optimum one, or the greatest one, is there, and the least is here. Oops. Guess we should follow directions. So color it in blue. Since waves extend in space, we don't get interference at one point, we get an interference pattern. What will determine the pattern is the distance to each source of waves. For instance, if two sources are in phase, crossing at the same time, then we'll get constructive interference whenever the distance to one source is an integer number of wavelengths more than the distance to the other source. By the way, for all of these things, we're assuming, and this is kind of crucial, same frequency, same wavelength. We don't talk about interference among signals that have different wavelengths and frequency. Here we'll see this phase argument from an acoustic source, where we have this person will be playing the same sound between two speakers, and then rig one of them to be out of phase.
Here I have two speakers, both connected to the same frequency generator, putting out a 200 Hertz tone. Between the frequency generator and the black speaker, I have a switch which will reverse the phase of the signal going into the black speaker. Now I'm going to set up the two speakers to face each other. Both signals going into the speakers are in phase. And the question is, when I flip the switch and change the phase of the signal going into this speaker by 180 degrees, what will happen to the sound coming out of the speakers? Will the amplitude increase? Will it decrease? Or will it remain the same?
So there we have them in phase, and so we're getting a pretty strong signal.
So as you can hear, or maybe you can't hear, the amplitude has been greatly reduced. This is because when the one speaker is out of phase by 180 degrees of the other one, the two sine waves add up to approximately 0 every place along the wave. Now, just to show that I haven't turned off one of the speakers, if I disconnect this speaker from the generator, the sound returns. And if I disconnect this speaker from the generator, the sound returns. Now, another question. What happens if I separate the speakers by some distance? What happens to the sound? Does it remain the same? Does the amplitude increase, or does it decrease further?
Now he's going to pull it away. They get out of phase, and they spike. I do wish he had gone a little further, because what he did there was found that they spiked a certain separation apart.
The amplitude did increase somewhat. This is because when I separated the speakers, there was another change in the phase between the two signals, and the two sine waves, the phases, became closer together than when they were out of phase by 180 degrees when the speakers were together.
Right. When he pulled them apart by half a wavelength, that introduced another 180 degree phase shift, which means they were suddenly back in phase and therefore would resonate. This is a mildly complicated picture, but the idea is we have something generating maybe sound waves or water waves or something with the same motion, the same phases, and this part is equidistant from the two. So whatever phase this gains by going this way, this gains the same amount. So we get constructive interference, or a high signal here. But this distance is 1/2 wavelength less than this distance, and so they cancel out. So we'd have no signal here. This distance here is 2 wavelengths less than this, it's a whole wavelength less than this, so that these would be constructive again. All right. List all the labeled points where the waves in the two sources constructively interfere. If there are no such points, state that explicitly. And then later on we'll do destructive. So we want to figure out, here are our sources, and we want to say, like, how far is let's say, let's make a little chart here. So let's say the point, distance to 1, and distance to 2, and therefore the change in the half. And these will all be in terms of wavelengths. So if I'm here, point A is 2 from me. But if I'm here, point A is 1, 2, 3, 4, 5. Although we should be careful here because actually these are, each box is half wavelength. So actually I should fix that because point A is 1 full wavelength away, whereas the other point is 1, 2, 3, 4, 5 half wavelengths, or 2.5 wavelengths. The difference is 1.5 wavelengths, so we'll call that type destructive. They would cancel out. On the other hand, point B is 1/2 from this guy, but then 1, 2, 3, 4, 2 from here. Their difference is also 1.5. And so also destructive. If we look at point C is 1, 2, 3, 4, or 4 half wavelengths or 2 full wavelengths away from that guy. On the other hand, I'm going to be a little more careful here. It's 1, 2, 3, 4 half wavelengths and 1, 2, 3. Right, so we go 4 up and 3 over. This distance is 5, or 2.5 full wavelengths. They differ by 1/2. This is also destructive. I'm going to change my symbol for destructive. I don't want confusion between point D and destructiveness, so we'll say instead that this is, we'll say there, destructive is unhappy. If I take location D is, it's 1/2 wavelength from the left one, but it's 1 full wavelength, which is half a wavelength here. Also destructive, sensing a pattern here. E is 1 full wavelength from the left source, but 1/2 from the right source, so that's half a wavelength difference. Also destructive. And boldly enough, I'm going to say it's probably going to be destructive as well, because F has the same issues as C did, which is that it's 2 full wavelengths away from source 2, but it's 2.5 wavelengths from source 1, so that's 1/2. Also unhappy. So this question's kind of goofy because they're all destructive. But let's see. Let's see if we could rig it a little differently. What if we had somebody? No, it's not that easy to find a spot. So we're gonna same kind of setup. Let's look at these. So now I'm going to say again, let's do the point we care about, which is A, B, C, and D, and the distance from the left one and the distance from the right one, the change in wavelengths, and the type. We'll do that. So point A is 1/2 wavelength from the left and 1.5 wavelengths, because it's 3 units, from the right. So we have 1/2 and 3/2. So delta L is 1 wavelength. So this is constructive interference. They would add up. All right. Part B is, point B is 1/4 wavelength from the source, because it's half a box, and each box is half a wavelength. It is, on the other hand, 1.5 boxes, or 3/4 wavelength away from the other source, which means the difference is 1/2 wavelength. This is destructive interference. If we look at C, C is 1, 2, 3, 4, 5 half wavelengths away from the left source, and 1, 2, 3 half wavelengths from the other. The difference of that is 2 half wavelengths or 1 complete wavelength. That is also constructive interference. And then finally for part D, it's going to be a little weird, but it is, well, equidistant, whatever this turns out to be. So this is 1/2 and 1. Let's see, 1 squared plus 2 squared. They're each root 5 halves wavelength. But that's 0 wavelength separation, and so they're all constructive. In fact, anywhere on that perpendicular bisector would be constructive.